But I cannot
So,
see the question. If there are questions, can you let me know?
okay.
Okay.
So it is my great pleasure to introduce now Paolo Bellingeri from Université de Caen Normandie, who will talk about congruence and crystallographic braid groups. So the word is to you, Paolo.
Okay. Thank you very much. I'm very happy to be virtually with you for this conference in honor of Lou. And as a student, as a PhD student, I think that as everyone, I study a lot of state sums, brackets, and so on. But as a researcher, I think that the most interesting result for me, once more as a researcher, was everything about virtual nodes. In fact, we are very happy that the talk before was of Lou, and the talk of Lou was about some combinatorial generalization of knots, because for several papers I studied virtual knots with some colleagues, welded knots, but also the braid counterparts, in particular virtual braids and welded braids. And for several papers, I tried to understand better this definition of virtual object, because it was clear from the topological point of view, but quite mysterious from the algebraic point of view. And finally, just 2 years ago, with Luis Paris and Laure Thiel, we found that finally, when you have the virtual braids, they have a real algebraical meaning using the root system of the braid group, and we were able to do some virtual extension also for other arting groups, and now also for cactus groups. So in some sense, it is also interesting to see that an topological intuition can become sometimes also an algebraical meaning. And my talk today will be about some groups related to the braid group, not extension, really some quotients and normal subgroup of the braid groups. So there are two families, the congruence braid groups and the crystallographic braid groups, which are quite noble because they were introduced by Arnold and by Titz, with, of course, different names. So this is a kind of a survey on 3 different papers with 3 co-authors: Celeste Damiani, Oscar Ocampo, which is here. So he will be able to answer if I'm not able, and Haris Stylianakis. So the first is appeared in Journal of Australian Mathematical Society, and the other 2 are submitted. So I will start with the braid group without giving any geometrical or topological interpretation, you know very well, but just let me remember that the usual good presentation that I think that you saw thousands of times. So we have n minus generators, sigma 1, sigma 2, until sigma n minus 1, that I remember that topological they are just a cross between the strand I and I plus 1. With the following relation: when the 2 generators are far away, strands are not involved at the same time, we have a commutation, sigma I, sigma j is equal to sigma j, sigma I, if the distance between I and j is greater than 1, and we have the usual relation ABA is equal BAB if they are on 3 subsequent strands. So sigma I plus 1, sigma I is equal to sigma I plus 1, sigma I plus 1. And let me also remember that the pure Braid group is the kernel of the canonical map from the BN to the symmetric group, where we see the symmetric group with the presentation that you see here. But we have also to add that generators are involutive. In topological, we are just saying that to sigma I, subalgebraically, we are saying that sigma I, we associated the transposition I plus 1. And the pure Braid group, or the dial Braid group, in the sense of Arnold, we make colored Braid group. It is this one, which are very well-known presentation, given, for example, by Artin himself, which is quite complicated, but there are much more geometrical and symmetric presentation. So let me go. The next one. Sorry. Okay, congruence Braid groups. There are several. Is going a little bit too. Okay, I will do like this. Sorry. So the congruence Braid group. Congruence Braid group are some geometrical subgroup of the Braid group, but here I will decide to define them just for a question of time in a very simple but maybe not so understandable way, like using the Bourau representation. I take the Bourau representation, so sigma I goes into this matrix where you have the identity, and then it is a 2 by 2 matrix y minus t, t 1, 0, and then still the identity matrix. And we evaluate this representation for t equal -1. Then we have an integral representation of Bn in GLN of Z, okay, on integral coefficients. And more than that, we have also that actually it is a symplectic representation of the Braid group. Let me say that we can do this result also with the geometry, using the double covering of the disk with n deleted points. But here, just for giving you how to find a representation of the Braid group in a symplectic group. And this the kernel of this map is sometimes called Braid-Torelli group, which let you understand, which is that this is the counterpart in the realm of braids of the Torelli group and the theory of mapping class groups. Here, the general mapping class group, you obtain Torelli groups regarding the action on the homology. Here it is something very similar, and it is the good analogy for the Braid group. But here we can go a little bit further, and in spite of taking symplectic matrices of Z, we can decide to take a symmetric matrix of Zm, okay? And then we have what it is called the level M congruent subgroup of Bn. What it is known about these normal subgroups. As I told you, the first result is given by Arnold, which proves that actually Bn2 is the pure Braid group Pn. For m equal 4, but we are doing a jump of almost 50 years, was given by Brandon and Margalit, that they found that actually Bn4 is isomorphic to the square of the pure Braid group. And very recently, in September, there was a result of Banerjee and Haxford that gave for almost every case, except you see with the case 2, we are still missing the case m greater or equal than 6. We have at least that this group are the group normally generated by a family of 1, 2, or 3 generators. Okay, for n equal 2 is clear. It is already the result of simply that because Bn is B2 is equal to Z. But for the other, you see that we can see to appear the the end power of the first generator, and then all generators of the Braid group, because they are all conjugated, and some full twist on 3 strands, sigma 1, sigma 2 to the power 6, on our 5 strands, sigma 1, sigma 2, sigma 3, sigma 4 to the power 10. Anyway, it is not known a good presentation for the congruence Braid group or a geometrical interpretation, except the case that we saw about Bn2 and Bn4, and we found a presentation for a very specific case, in the case that with 3 strands. But I don't want to speak really about that, but I want now to show you the other family of groups that we were interested in. So, before explaining what it is a Braid crystallographic group, let me remember a definition, which is quite complicated. That a group is a crystallographic, is a discrete uniform subgroup of Rn with the semi-direct product of the orthogonal group of Nr. You see, it is quite complicated. I didn't give all definition, but hopefully there is a lemma that say to us that actually we can take as a definition that a group is said to be crystallographic if there is a exact sequence where this group G is the middle group. We have a surjection on a finite group, and the finite group acts on the kernel faithfully, and the kernel is a Cartesian product of copies of Z. If you have, if you want to have a very simple example, you can take the wallpaper groups. Wallpaper groups are a subfamily of crystallographic groups. So I don't want to say more about the first definition, sorry. Okay, sorry. There was a problem. Sophia, is okay for you? Do you see?
Yes, yes, and hear everything.
Okay, so there's, I don't know why. Okay, I will take back the diaporama. Sorry. So this will be our definition, okay? So a group which has an exact sequence between a finite group and a 3 abelian group. So let me recall that if we have a group G, I will call commit bracket GG the commutator subgroup of G. And there is very nice result independently found by Beckenmarin and Gonçalves Guassi Ocampo, that the quotient of the pure Braid group, not over Pn, because the Bn over Pn, we have the symmetric group, okay? So everything is very well known. But if we take a Bn quotiented by the commutator of Pn, we have a new group. It is a new group is crystallographic, and more precisely, we have a T-exact sequence where the middle group is our crystallographic Braid group. The quotient is the symmetric group Sn, and the kernel is the abelianization of the pure Braid group. So it is very well known that the abelianization of the pure Braid group is Z to the power n minus 1 over 2. And as I told you, this group was introduced by Jacques Tits as Group de Coxeter étendu. Because like AK algebras, you can see AK algebra like the formation of the algebra of the symmetric group, or you can see as the quotient of the algebra of the Braid group. So from the point of view of Gonzalez, Kwaski, Marino, Ocampo, we can see this crystallographic group as a quotient of the Braid group Bn. But for Tits, it was quite an extension of the Coxeter group, in this case, the symmetric group, by a free abelian group, which is, for him, was finally also the abelianization of Pn. What it is funny about this group is that you can have only some kind of torsion elements on the group. It is not finite, but there are some torsion elements which are completely classified. And you can do this, construction for almost every generalization of Braid group. You can do for surface Braid group if you want to do some topology. If you can do with a complex reflection group, all other arting group, if you like algebra, but also for some general, some combinatorial generalization of Braid group. But in this case, things are much less interesting. For example, in this case, if you, in spite of writing Pn and Bn, we take the virtual pure Braid group and the virtual Braid group, or the welded pure Braid group and the welded Braid group. The sequence that you have, that we have here, actually, it was already a semi-direct group, some semi-direct product at the level of the virtual Braid group and the welded Braid group. So, in the case of virtual Braid group and welded Braid group, this sequence gives simply that it is a crystallographic group, also in the virtual and the welded case, but it is simply a semi-direct orbit of the symmetric group acting on an abelian, free abelian group. So this is really for the most interesting case is for surface Braid group, arting Braid groups, and the Braid groups. So let me say also something else, because actually it was a not conference. So here the counterpart of this object will be fused links, which were introduced by Lou also. But I have no idea what are some counterpart for congruence Braid groups. So the idea is to replace the pure Braid group and to use a congruence Braid group, because we saw that Arnold showed that the pure Braid group is the congruence subgroup Bn2. But now we have a family of subgroup of Bn, which are all included in Pn, at least when n is even. And so we can ask what it is relation between congruent subgroup and the crystallographic groups. So we started to study this problem with Celeste, Oscar, and Harris, and we have some partial result. For example, if we are at the case that n is an odd integer and m is a prime number, we have that if the abelian group, okay, the abelianization of the congruent subgroup is torsion-free, then the quotient Bn by not the commutator of Pn, but now the commutator of any congruence subgroup under condition on n and m that I said before, we have this crystallographic. and with the dimension equal to the rank of the abelianization. Of course, this is a result about if the abelian group is torsion-free. Very few is known about that, because we know, for example, just at the end of this line, you can see that finally we know that about Bn2, of course, because it's the pure Braid group, and we know about the case on 3 strands for some p prime. But and the other point is that the classical technique do not apply, meaning that the result of Warsky, Gonsalves, Ocampo doesn't work here, because the industrial representation on the abelianization of a concurrent Braid group is not injective. It's much more complicated than in the case of the abelianization of the pure Braid group. So this is the first complicated point. Then we have quite a technical result about the fact that we take the crystallographic group, the usual crystallographic Braid group, Bn over the commutator of Pn, and we take a kind of a counterpart in the realm of any congruence subgroup. So we take a map on the congruence group BNM over the intersection of the congruence group itself with the commutator of Pn. They can be quite strange groups, but actually we're just giving a map from and that send any sigma I, any generator of the group of the Braid group, but here we have to find that it is the equivalent class, because we are not in Bn, but we are in the quotient Bn by the commutator of the pure Braid group, and we send every sigma I into sigma I to the power m that we saw to be an element of the corresponding congruence Braid group. And then we found that if m is odd, actually this map is an isomorphism. And then we have that in this realm, finally, we are able to find some crystallographic group, but not on the Braid group, the quotient of the group, but the quotient of the congruence Braid group. But the funny result is that in this proof, we were able to say that the crystallographic Braid group is not co-option. I remember that a group is called co-option if it is not isomorphic to any of its proper subgroup. But Bn over Pn is isomorphic to a proper subgroup, because the group Bnm over the commutator Pn intersected with the congruence Braid group is a subgroup, and it is isomorphic. We were able to find a proper subgroup of the crystallographic group using congruence Braid groups. Something similar, it is already true for the Braid group, because the Braid group is Hopfian. So every surjective homomorphism from Bn to Bn is also injective, but Bn is not co-option, meaning that there are some injective endomorphism from Bn to Bn which are not surjective. So of course we can go a little bit further, and we can study not only the commutator, but we can study the lower central series of a group. So, for example, the first step was the group, the second step was the commutator, and then by induction we can define gamma kg like the commutator of gamma k minus 1g with g itself. So we are studying the lower central series of a group G. Once more, there is a quite mysterious definition of a quasi-crystallographic group using once more, I forget before to say that N was a simply connected nilpotently group, and then we have a maximal compact subgroup of the automorphism of N. And then we say that every uniform discrete subgroup of E on the semi-direct product of N by C. But once more, it is there is a result which gives us a much easier definition. And if we take a polycyclic by finite group, so what it means it is that a group which has a finite index subgroup which is a polycyclic, then E is almost crystallographic. This group E is almost crystallographic if it only has an nilpotent subgroup and possesses no non-trivial finite normal subgroups. So it is really a generalization of the notion of crystallographic group. Why that? Because Gonsalves, Guasios Campo, they found also that when we replace the commutator of Pn with the lower central series of Pn, we have a family of quotient of the Braid group, which are all almost crystallographic. So, of course, our idea was to say something similar for our new friends, the Congruence Braid group, but we were able to do very few results, in the case on 3 strands. In some sense, my talk is also an invitation to join us to try to find a new result of this kind, because we were able, in the case the P is an odd prime, so P is different of 2 or P is equal to 4, we were able to say that B3 over the K term of the central series of the Congruence Braid group on 3 strands of level P is almost crystallographic. And in a very particular case, for P is equal to 3, we were also able to calculate a presentation and to find that this group is almost Bieberbach. Like usual, we say that a crystallographic group is Bieberbach if it is torsion-free. We say that an almost crystallographic group is almost Bieberbach if the group is torsion-free. I will not speak about holonomic group, but simply that we understand very well this group. But of course, as you know very well, the case of the Braid group on 3 strands is very particular. So it is probably we think that things will become very much more complicated for more strands. And let me finish just for saying that all these groups, as we saw, they are related to the power of generators. So let me take the normal closure of sigma 1 to the power m and the Braid group Bn. It is very easy to show that the normal closure of sigma 1, 2 is Pn. So we have a third definition of the pure Braid group as the normal closure of a particular element of the Braid group. Coxeter himself studied the case of m greater or equal than 3, asking about the fact if the quotient of Bn by sigma 1 to some power, if it were whether it was finite. And in another way, if the index of the normal closure of sigma 1 to the power m was finite. And finally, he found a very nice formula, which is exactly the formula for regular tilings on the plane. So m minus 2 and minus 2 less than 4. And so finally, we have this situation that, of course, the first case is that when sigma 1 to the square, we have the symmetric group. Everything is very well known. What it happened for the other ones? So when we have like for you see like for the tetrahedra, the octahedra, the dodecahedron, and so on, we have the result that all these groups are finite. They are the only ones which are finite, and everything is very well known about these groups. So, but once more, in our case, congruence Braid group are all of finite index in the Braid group itself, because they are the kernel of a surjection of Bn over a finite group, a symplectic group with coefficient z over z, mz. So finally, the last result that we studied was about the relation between this Coxeter group, meaning the normal closure of sigma 1 to the power m, and congruence subgroup. So finally, we can, the first fact is that, as I told you before, the congruence group contains all the time the corresponding normal closure of the good power of sigma 1. And then we found that the Coxeter Braid group has finite index in the congruence Braid group in exactly the same case. Of course, that this is a easy result of algebra that they are finite index if and only if we are in the same case than the Braid group. And we studied the quotient in the finite case. And of course, Coxeter gave the result that all the other cases, this quotient were not finite, but we were able to say something more. We were able to find that actually the quotient of the congruence Braid group over the normal closure of sigma 1 to the power m contains a free group for very just a very specific case are outside of our studies. And I think they finished.
Thank you. That was a very interesting talk. Thank you very much, Paolo.